सर है, सर की ऑडियो नहीं है सर। सर सर पढ़ाना शुरू कर दिया है, सर को आवाज नहीं आ रही।
सर आप
सर सर हेलो हेलो।
भाई वो उनका मेरे ख्याल से वॉल्यूम लो हुआ है।
So, in the previous lecture, we were discussing about the properties of determinants. A few properties we had discussed. Let me remind those properties. If the first property we discussed, the determinant of a transpose of a matrix is equal to the determinant of a matrix. If any one row or one column it has all the entries 0, then the determinant of a matrix is 0. If two rows or two columns are identical or a scalar multiple of each other, then again, the determinant of that matrix is 0. Because if one row or one column is a multiple of each, some other row or column, then we can make one of these two columns or rows 0 by applying simple one binary, it's an elementary row operation. Some other properties I discussed with you. We can take a constant from a determinant from any one row or any one column from the determinant. And the property which we discussed, that the determinant of a transpose of a matrix is equal to the determinant of A. This basically tells us that just like the elementary row operations in determinants, we can apply elementary column operations as well. Okay. So the elementary column operations are also allowed in the determinants in order to reduce them into H-len form. Still, is there anyone who is not listening me? Is there still a problem? Imtiaz, can you listen me now? Check your mic and headphones. Okay, I hope there is no problem. Now, which we discussed in the previous.
सर आपकी आवाज क्रैक बहुत ज्यादा कर रही है, जरा हेडफोन की वो ठीक कर लें। अगर आपके फेस को टच करो, उसको थोड़ा दूर कर लें।
Oh, right. So I think that's fine now. Now, another property which is we discussed that if the third.
सर आपकी आवाज काफी ब्रेक हो रही है.
What was the third elementary row operation in the matrices? In the determinants. That we can add a multiple of one row to some other row. That operation which we apply in, for example, when we say that alpha times Ri plus Rj. In that case, the row j will be changed. This was the third elementary row operation in determinants, which doesn't change after applying this elementary row operation. The determinant of the resulting matrix, which is a new matrix, after applying this operation, we get another matrix, another determinant. In that case, this determinant is basically equal to the determinant of previous matrix. This was the third elementary row operation. Why is it so? If we look at, for example, A11, A12, A13, A21, A22, A23. Now A31, A32, and A33. Okay. Now apply this kind of elementary row operation on this matrix. What would happen? For example, I say that I multiply first row and add it to the second row. What will change? Row 2 will change. So the new matrix, which is the matrix B, so determinant of B, it becomes A11, A12, A13. Second में क्या आएगा? A21 plus K times A11 A22 plus K times A12, and the third entry would be, let's A13. So A23 plus K times A13. So this is what we have applied this operation A31, A32, and A33. Now, can you tell me whether this determinant of this matrix would be equal to this determinant of this? Would it be same? Anyone?
सर आपने ऐड किया?
Yes.
नहीं सर सेम नहीं आएगा.
ऐड किया है सेकंड फर्स्ट रो को कांस्टेंट से मल्टीप्लाई किया है और ऐड किया है सेकंड रो में. So the resulting determinant,
सेम होगा.
would it be same as the previous determinant?
Yes.
सर जिस नंबर से मल्टीप्लाई किया है उसी से शायद मल्टीप्लाई हो.
उसको तो बाहर लेके आना, उसके बाद उस होएगा. वो तो रूल है ना आपका, जिसको तो मल्टीप्लाई करो उसको बाहर डिवाइड करना.
No, that is
वो तो तब उधर जब एक रो करना होता है.
हाँ, जब किसी एक रो को आप किसी कांस्टेंट से मल्टीप्लाई करते हैं तो बाय डिवाइड करते हैं. That is a different case. That is other elementary row operation. Now
Yeah,
I'm talking about this elementary row operation. What would happen? Would the value of this determinant change?
No sir.
No. Why?
सर क्योंकि आई थिंक कोफैक्टर एक्सपेंशन जब आप करोगे इसकी टेक्निकली तो वो
No,
end result
yeah,
इसके
no. In the previous lecture, we discussed a property that A11 plus B11, हमारे पास A12 plus B12 और A13 plus B13 है. ठीक है, और बाकी यहाँ पे A21, A22, A23, and then A31, A32, and A33. How can we expand this determinant? Can we expand it, split it into two determinants?
Yes, sir.
हमने ये previous lecture में पढ़ा था ना?
जी जी.
Now, if you expand this determinant into two by writing the first entries in the first matrix, sorry, determinant along with these entries, and the second determinant along with the second entries. So this property is true. I hope I told you in the previous lecture. I hope you remember this. We can separate these two determinants. Now, if you use this property on the above determinant, what would happen? You can again split this row and you can write this determinant into sum of two determinants. Yes? A11, A12, A13. Then A21, A22, and A23. And then A31, A32, and A33. Plus ये second entries, ये वाली. ठीक है, बाकी वही रहेगा. यहाँ पे K आ गया A11, sorry, K21. हाँ, K11, K12, and KA13. ऊपर वाली लाइन क्या है? 11, A12, A13. नीचे वाली क्या है? 31, 32, and 33. Now, यहां से आप इस रो में से K कॉमन ले लें तो क्या होगा?
अच्छा समझ आ गया सर. तो
इस डिटर्मिनेंट की वैल्यू क्या होगी?
सर 0 होगी क्योंकि वो दो रोज सेम हो जाएंगे ना. तो
फर्स्ट टू रोज सेम हो जाएंगे अगर आप K को कॉमन लेंगे तो इस डिटर्मिनेंट की वैल्यू 0 हो जाएगी. इट मींस जो हम ये एलिमेंट्री रो ऑपरेशन लगाते थे तो उससे डिटर्मिनेंट पे हमने कहते थे कि कोई इफेक्ट नहीं पड़ता उसकी वैल्यू पे. सो दिस वाज द रीजन कि क्यों इफेक्ट नहीं पड़ता. बाकी दो एलिमेंट्री रो ऑपरेशंस अगर आप अप्लाई करें ना, दो रोज को इंटरचेंज करें या दो कॉलम्स को इंटरचेंज करें तो वी हैव टू पुट अ नेगेटिव साइन आउटसाइड दैट डिटर्मिनेंट. और दूसरा क्या था एलिमेंट्री रो ऑपरेशन कि अगर आप किसी एक रो या कॉलम को किसी कांस्टेंट से मल्टीप्लाई करें तो यू हैव टू कंपनसेट दैट कांस्टेंट एंड यू हैव टू डिवाइड इट आउटसाइड दैट डिटर्मिनेंट. कंपनसेट करना है. लेकिन इस ऑपरेशन से डिटर्मिनेंट की वैल्यू पे कोई इफेक्ट नहीं पड़ता. I hope you know now why this operation does not change anything in the determinant. I hope you get it. Because यहाँ पे ये जो determinant है इसकी first two rows जो हैं वो एक दूसरे का constant multiple हैं. means they could be identical. Or we can make one row entirely zero row, which contains all the zeros. So the determinant of this thing will be zero. So this is what I wanted to tell you. कि तीसरा elementary row operation जो है वो उसका effect क्यों नहीं होता. I hope you get it. If you have any question, you can ask me. So another very important kind of property is that if we have in any row, if we have alpha A11 plus beta B11, okay, alpha A12 plus beta B12, and alpha 13 plus beta B13. So it's basically the first row is linear combination of two numbers. I'll tell you later on what is linear combination. You can say that it's a constant multiple of B11 and so on. The rest of the entries are A21, similar A22, A23, then A31, A32, and A33. So we can split this whole matrix into two matrices. Okay. The first one
कि
we
आवाज
write
अभी
the
भी
first.
बहुत ज्यादा कट रही है और फट रही है, वो उससे बहुत डिस्ट्रैक्टिंग है, समझ नहीं आ रही कुछ रियलिस्टिकली.
सर ख्याल में माइक का मसला है.
So इसे डिस्कनेक्ट करके रिकनेक्ट करें.
So it happens, I think, when I go towards the board, maybe.
जी जी अब सही आ रही है.
अब सही आ रही है ना? What should I do then? Let me put this laptop near to that board, or should I use the central boards maybe? Central boards यहाँ पे शायद जो
हाँ
है.
जी सर, मैंने भी यही रेकमेंड करा था क्योंकि आप लेफ्ट से शुरू कर रहे हैं तो ये सेंटर वाला बोर्ड यूज करना शायद इससे बेहतर है.
Let me use the center boards. Then I hope it will be better. Let me change the orientation of the camera. Let me discuss that thing, finish that thing, and then we'll move towards the second board. Okay. Now we can split up similarly first row into sum of two determinants, and then we can take alpha common from the first row and beta common from the second row. So we can split this determinant into two different determinants, A13, A21, A22, and A23, and so on. Okay, plus beta times B11, B12, B13, and A21, A22, A23, and so on. Okay, the same entries. So we can split this determinant into sum of two determinants in this way, okay, as well. Now let's come. These were basically the properties related to the previous lecture. Now we are going to discuss some other basic properties of the determinant. If you have any question regarding this thing, you can ask me. Now, another property which let us say that this is the third property, maybe. Determinant of product of two matrices, provided that their multiplication is possible. Okay, and then its determinant is equal to the product of their individual determinants. Okay, even we can generalize this this identity as if we have n matrices, A1, 2, so on, n. Then even then the determinant of product of these n matrices is equal to the product of their individual determinants. This is another property of determinants which we can use this thing. Okay, but remember that it is very important. Many students do this mistake that the determinant of A plus B is not equal to determinant of A plus determinant of B. Okay, remember this. Don't assume that if this property is true for the multiplication of two matrices, then it would be true for the sum of two matrices. So this property is not in general true. So determinant of A plus B is not equal to determinant of A plus determinant of B. Remember this. And I told you another property, determinant of A transpose is equal to determinant of A. What this property tells us that the elementary row operations which we apply on A, because the determinant of transpose of a matrix is equal to determinant of A, it means that if we interchange the rows into columns and again apply the elementary row operation, it is equivalent to apply the elementary column operations on the original matrix. Okay, so these things are possible. So in order to reduce any determinant to echelon form, we can apply a mixture of elementary row operations as well as elementary column operations. But these mixture of operations, they do not preserve many properties of determinants which we need in subsequent topics. This is only basically possible while finding the determinants of some matrices. If you want to compute some row space or column space of a matrix, which we'll discuss in upcoming topics, then we cannot apply a mixture of row operations and column operations in order to find the whatever we find the determinant of a matrix if we want to preserve some other property. But if you want only to find the determinant, then you can apply the mixture of operations of row operations, elementary row operations, and elementary column operations. I hope you get it. If there is some other property which I am forgetting, let me see. There is another property which is determinant of A inverse is equal to 1 over determinant of A. Okay. So this is another property which you have to remember. You can prove it, but how can we prove it? For example, we know that A inverse into A is I. Okay, for all invertible matrices. If A is a square matrix and its inverse exists, then we can write A inverse into A is equal to I. Taking determinant on both sides, determinant of A inverse times A is equal to determinant of I. Now, what would be the determinant of I? Someone tell me. 1, because it's a diagonal matrix. In a diagonal matrix, the determinant is product of its diagonal entries. So its determinant is 1. Okay, this is 1. Now, this is basically the product of two matrices. We can apply that this property. We can separate this determinant. So determinant of A inverse times determinant of A. Okay. Now you can see that determinant of A inverse is equal to 1 over determinant of A. So we can easily prove these properties. It's a matter of basically just it involves a little bit of algebra and some of the properties of determinants. If you are interested in proving these properties, you can see their short proofs in the books, but not interested in the proofs of these properties.
So
you just have to remember.
Included, no?
Not yet, but I'll think about it. So you can prove these properties, okay, very easily. You don't worry about it. These are very simple ones. Now, let me repeat it. Determinant of C times A is equal to C power n determinants of determinant of A. I told you this one in the previous lecture, I think. I remember now. Yes, I told you. I don't think आपको
नो
पिछला
सर
lecture
नो
पिछला lecture जो है वो याद है. चलें कोई बात नहीं. देखिए डिटर्मिनेंट में से अगर आप किसी एक रो में से कांस्टेंट बाहर लेते हैं A12 CA13 ठीक है, तो CA21 CA22 sorry A23 not C here A33 sorry A31 A32 and A33. So this
ये
is
वही है ना कि जितनी रोज
we
में से
can
आपने कॉमन लिया उतनी उसकी पावर हो जाएगी.
हाँ, अगर आपके पास एक रो में C है तो एक रो से बाहर आएगा. अगर तीन रोज में ये सारों के साथ C है, तीनों रोज से आएगा तो C क्यूब हो जाएगा ना यहाँ पे. बाकी अंदर आपके पास एंट्रीज A11 A12 A13 सो ऑन, बाकी वो एंट्रीज आ जाएंगी. ठीक है. सो यहाँ पे क्या है, C मल्टीप्लाई आ रहा है A के साथ और A इज सम मैट्रिक्स ऑफ ऑर्डर n, वी अस्यूम इट. ठीक है, A is a square matrix of order n. Then how many rows this matrix have? It has n rows, so C power n will come out. Okay, one C from each row. There are n rows, so we must have C power n into the determinant of A. Okay, by assuming that A is a matrix of order n. I hope you get it.
सर ये ऑर्डर n इसलिए है ना क्योंकि जब हम एक रो को एक चीज से मल्टीप्लाई करते हैं तो बाहर भी एक दफा लिखा जाता है. अगर आप दो रो से करोगे तो वो चीज दो दफा बाहर लिखी जाएगी.
You can say that. मतलब अगर इस तरह का है, देखिए यहाँ पे C टाइम्स A क्या है? It's a simple multiplication of scalar with the matrix. C टाइम्स A का मतलब क्या है कि C को आप A की जितनी भी एंट्रीज हैं उन सब के साथ मल्टीप्लाई करोगे, तो ये C सब के साथ आएगा. अब जब आप डिटर्मिनेंट लोगे इसका, तो C को आप बाहर कॉमन लोगे तो हर रो में से एक C बाहर आएगा ना, तो जितनी रोज होंगी उतनी C की पावर आ जाएगी. ठीक है, because the multiplication of a scalar with the matrix is a different thing, but multiplication of a scalar in the determinant is a different thing. जब किसी when you multiply a scalar with the matrix, then you have to multiply that scalar with each entry of that matrix. Whereas when you multiply a scalar with some determinant, then you multiply that scalar with only one row of that determinant. You don't have to multiply that scalar with each entry. So scalar multiplication in matrices is different from the scalar multiplication in determinants. So remember this. I hope you get it. Any confusion? Okay. Then let's do a couple of examples of these properties. How can we use these properties to simplify the determinants or to find the determinants of some matrices? For example, find the determinant of this matrix A, B, C, and D, E, F, 2A, 2B, 2C. So what would be the value of this determinant? You have to keep all the properties of the determinant in your mind so that you can quickly find the determinant of any matrix. So anyone, tell me what would be the value of this determinant?
तो पहले तो हम A को कॉमन ले सकते हैं, A और B और C को.
A और B, C को कॉमन ले सकते हैं.
0 होगा
क्यों 0 होगा भाई?
क्योंकि
फिर
2
zero होगा.
कॉमन लेंगे तो वो
हाँ.
रोज सेम हो जाएंगे.
मल्टीपल्स हैं तो रोज
हाँ,
एक दूसरे
2
की.
को कॉमन लेंगे, सॉरी.
0. Why? Why? You have to justify your answer. Okay. Because the first row and third row are constant multiple of each other. Okay. First and third rows are constant multiple of each other. what happens when two rows are constant multiple of each other? We can subtract a multiple of 2 of this row from this row. We'll get a 0 row. Okay. So if we have a 1 0 row in the determinant, then the value of determinant is 0. Okay. Now let's have another example. Maybe this one. Negative 3a, negative 3b, negative 3c, d, e, f, g minus 4d, h minus 4e, I minus 4f. Okay. What would be the value of this determinant? Anyone? You don't have to evaluate this determinant. Okay. You just have to use the properties in order to simplify this determinant and try to find the value of this determinant.
Sir, you can break it down into two matrices, and
Two
then
determinants. Into two determinants, not
you can, yes,
matrices.
two determinants, and then you can
The
take
first two rows would remain same. The third row, G, H, I. And here the third row would be negative 4, negative 4,
So
D,
you can just negative 4
negative 4,
common.
E, negative 4, F. And in the next step, you can take negative 4 common. ठीक है, negative 4 common ले लें आप next step में से, यहाँ पे आपके पास negative 4 आ जाएगा. Now you can see that the second and third row are identical here. So the value of this determinant would be 0, and we are left with only this thing, which is not possible to simplify further. So this will be the value of that determinant. Okay. With the alphabets, we cannot simplify further that determinant. So this will be the answer of, or the maximum simplification of the above determinant. Let me show you another example, which will definitely give you another kind of 2, 8, 1, 4, 3, 2, 5, 0, sorry, 1, 1, 10, 6, 5, 4, negative 6, 4, negative 3. Now, its value is 0. Tell me why. Anyone?
सर क्योंकि second column और third column एक दूसरे के multiples हैं.
Second and
Column.
second column and
Sorry, fourth column. 4, 1, 5, minus 3.
okay, this is a column, this is a column, C4, and this is C1. We can see that C4 is 2 times C1. Okay. C4 is 2 times C1, so its value is 0. Because the column 2 and column 4 are multiple of each other, a scalar multiple of each other. So the value of the determinant is 0. That is the reason. Okay. I hope now you get you understand what is the importance of these properties. You have to remember this. You can solve determinants very easily and very quickly by keeping these properties in your mind. I hope you get it. If you have any question, you can ask me. Any question? No question. Now, we have discussed several methods, means at least 2 methods of how to find the determinant of a matrix. A cofactor expansion and this elementary row operations, reduction into echelon form. You can apply a mixture of row and column operations. but only in this case if you are interested to find the determinant only. Okay. The third thing is we can use properties to find the determinant as well. These properties help us to quickly find the determinant, to quickly solve the determinant and find the value of the determinant. So we can use the mixture of all these. We can use elementary row operations, we can use cofactor expansions, we can use properties of determinants in order to find the value of determinant as quickly as possible. Okay. So this is your choice that at any stage or at any step, what method you use. You apply an elementary row operation at a particular step, you apply a cofactor expansion, or you can use some other property of the determinant. You have to find it as quickly as possible. Okay. So there are a couple of more exercises here on this last slide of lecture 5. You can do these questions as well for your practice, and you can have more these kind of questions in the book as well. Is there a question in the chat window? C1 is yes. C2 is 2 times C4. This one. This is not C1, sorry. This is C2. अब ठीक है. Thank you. Yes, it is C2 is equal to 2 times C4, not C1. Any other question? No, if you don't have any question, let's move to the next thing which we need to discuss. These were the properties of determinants. There are some other properties which we need to discuss about inverse of a matrix and transpose of a matrix, about the symmetric matrices. There are some other properties which I'm going to tell you very briefly, and I would advise the TAs to discuss them in detail with the help of examples in tutorials. Okay? Try to attend the tutorials as well. Some of the easy things which I don't discuss here in my lecture in detail, I request and advise TAs to discuss those things in detail during the tutorials. Okay. So some other properties which are important to discuss. For example, the first thing, properties of inverse of a matrix. Obviously, we will assume that A, B, or any other matrices are square and invertible matrices. Okay, square invertible matrices. Then we discuss their property. The first property is the double inverse of any matrix is the same matrix. Okay, if you take inverse of any particular matrix 2 times, okay, double inverse of a matrix, it gives us the same matrix. Okay, so next is A into B whole inverse means if we have a product of 2 matrices, its whole inverse is equal to B inverse times A inverse. Okay, their order will be interchanged. Or we can generalize this property as well. If we have 3 matrices, A into B into C, whole inverse, then their inverse would be C inverse, B inverse, A inverse. So it's a kind of cyclic kind of rotation in the matrices while separating the inverse. Or even more, if we have n matrices, A1, 2, so on, An, and we are interested in finding its inverse of all this thing, then their order will be interchanged. There is a kind of cyclic rotation of these. You can say that the matrices A inverse into A n minus 1 inverse, so on. into A2 inverse into A1 inverse. So remember this property. We'll use these kind of properties in subsequent topics. Another, what else can I tell you? Let me revise these things. Let me see these things from some of the lecture. These properties are basically listed in book as well. You can see them from there. A inverse whole inverse equal to A, AB whole inverse equal to this, and we can generalize this property. We can generalize this property for n matrices as well. Some other properties related to the transpose, I remember I'll tell you more properties. But in tutorial, I definitely advise TAs to discuss these properties in more detail with the help of examples. So you can here say that the transpose, double transpose of a matrix is again the same matrix. But here we don't have this kind of restriction. A and B are scalar and invertible matrices. Here A is any matrix. A is any matrix of any order. It can be of any order. It can be a rectangular matrix, it can be a square matrix, it can be a row vector or column vector or anything. We don't have any restriction on this. The double transpose of a matrix is again the same matrix. Okay, the next property is similar to this one. If we have A into B whole transpose, this is equal to B transpose into A transpose. Okay, but remember that this product should be multiplication should be possible. Multiplication is possible. So when is a multiplication of two matrices is possible? Anyone? Can you tell me?
The columns of the first row are equal to the
Yes.
rows of the second row.
Yes, column of the first matrix should be equal to the first rows of the second matrix. So this product should be possible. Then we can say that the transport of the product of these two matrices is equal to B transpose A transpose. Similarly, we can generalize this property as we have generalized this one. So if we have n matrices, for example, A1 into A2, so on into an whole transpose, then the order of the matrices will be changed. So this will be equal to an transpose into an minus 1 transpose, so on, A2 transpose into A1 transpose. Okay. Couple of more properties maybe for the transposes, not determinant. I've been writing determinant in the two lectures. Yes, A plus B whole transpose is equal to A transpose plus B transpose. This is true for the transposes, or even plus or minus. Okay, this property is true for the transpose. Okay, but this is not true for determinants and inverses. A plus B whole inverse is not equal to A inverse plus B inverse. That is also not true as in the case of determinant, because the determinant of A plus B is not equal to determinant of A plus determinant of B. But in transpose, this property is true. Any other property which I could remember is I don't remember. So you can read these couple of more properties you would have in the book, and also in my notes, you can read from there as well. Okay, if you have any further question regarding the properties of matrices, determinants, inverses, transpose, and symmetric matrices, you can ask me any question.
सर वो हमने एक थ्योरम पढ़ा था ना जिसमें था कि वो जो अभी भी अप्लाई किया था कि ट्रायंगुलर मैट्रिसेस का जो होता है उनमें उनका जो द डायगोनल एंट्रीज का जो प्रोडक्ट होता है
product.
वो उनका डिटर्मिनेंट होता है लेकिन
Yes.
so but the trace is the addition of all of the diagonal entries, right? It's not the product.
Yes. Trace of a matrix is something different.
Sahi.
Trace is the sum of diagonal entries, whether the matrix is diagonal matrix or not, whether it is a scalar matrix, whether it is an upper triangular matrix, lower triangular matrix, or the normal matrix. Trace is just the sum of the diagonal entries of any matrix. But the matrix should be square, because unless you have a square matrix, you cannot identify the main diagonal.
Okay.
Okay. Okay, this is all stuff is very easy. I hope you all would have grabbed it, these concepts. These are easy things. That's why I'm gonna quickly, I wanted to quickly review these properties. You can prove these properties. You can see the proofs from the book as well. The proofs are not very lengthy. They are very easy. If you are interested to see the proofs. Is that it? What does it mean, Mohid Ali?
सर मैंने अपने हेडफोन्स उतारे थे, मुझे लगा था आप कह रहे हैं कि आज का लेक्चर खत्म हो गया, किसी को इतनी अच्छी नहीं लगता।
नहीं, ये वाली खुशखबरी जो है ना आपको शायद आखिरी लेक्चर्स में मिल जाए, अभी नहीं। वी हैव टू डू लॉट ऑफ थिंग्स।
सर
जी बेटा।
सर वैसे ट्रेस का फायदा क्या होता है, लाइक ये यूज किधर होता है, ट्रेस क्यों फाइंड करना होता है?
यार वैसे तो पूरे मैथ्स का कोई फायदा नहीं है, आपको पता ही है। कभी जिंदगी में यूज किया मैथ्स? हाँ
सर कर सकते हैं इंटीग्रेशन।
इंटीग्रेशन कर, लेट मी। Now we are going to discuss vectors. Vectors in space, in n space sometimes, or sometimes space. Okay, n space is basically also called as Euclidean space. Okay, Euclidean space. Okay, and Euclidean space is all, sometime you can say Rn is what? Rn is a n space. ठीक है, और इसको या हम यूक्लिडियन स्पेस भी कहते हैं, यूक्लिडियन स्पेस और n space. Okay, now what is this thing, n space or Euclidean n space or Euclidean space? All these names are basically same for one thing. Voice lagging. Is there any issue of voice now? To anyone? No? Okay.
No, sir, it's fine.
Okay, what is this kind of space and what are the vectors in this space? आप लोगों को पता होगा real line क्या होती है? R. Real line is what? It is nothing but negative infinity to plus infinity open interval. It contains all the real numbers. Okay. And what is R square? R square is what? It is R times R. And what is R times R? It is a Cartesian product of two sets. I hope आप लोगों ने intermediate या A levels में, O levels में पढ़ा होगा. What is the Cartesian product of two sets? So this Cartesian product is basically defined in a way that it has all the elements of these kinds. This is called ordered pair, such that X, Y belongs to R. This is the set of Cartesian product. Cartesian product means we are multiplying elements of two sets and we are putting them in ordered pair. Ordered pair क्यों कहते हैं इसको? Because we cannot change the order of these elements. That's why we call it ordered pair. We cannot change the order of the elements here, because if we change the order of these numbers, the meaning of this ordered pair will be changed on XY plane. What is the graphical interpretation, graphical representation of this R square? Graphical representation of R square is, it is basically XY plane. Here you put X, here you put Y. Okay, it's basically not X. It is, they are both mutually perpendicular real lines. Okay, mutually perpendicular or mutually orthogonal lines, because they are making 90-degree angle from the each side. So this is your R square. Now, what is R cube? What is R cube? It is nothing but the product of R 3 times. And what is the graphical interpretation of this thing? It is X, Y, Z. And this is what? This is basically a mutually perpendicular 3 lines. Okay, because they are making 90-degree angle with each other. So any element of this R square is usually, any point in this R square is denoted by X, comma, Y. Okay, and here any element in this, any point in this R cube, or we call it 3D space. Okay, we call it 3D space, and we call it 2D space. Okay, or 2D plane or XY plane. Many names are basically are in the market for these kind of things. Now, any point here in R cube is denoted by X, Y, Z. Okay. Now, can you ever imagine, okay, what would be R4? Okay. R5, R10, R15. No, you might have never imagined that. But if we look at this pattern, R is a single line, R2 is, it is graphically I'm talking about. It's a mutually perpendicular 2 lines. R cube is what? Our 3D space is what? It is mutually perpendicular 3 lines. They are making 90-degree angle with each other. Now, if we define R4, what would be, what can you think about it? What would R4 look like? Anyone?
सर इस तरह सोचा जा सकता है कि ये अगर
I read somewhere
स्पेस
that
है ना,
हाँ, हाँ.
तो वो स्पेस टाइम अगर जैसे वो R4 डायमेंशन अगर हम उसको कंसीडर करें.
No, that is a separate thing.
yeah,
Time
that's
is
the dimension in which you
some
can't
other
point.
definition. Okay, time is an invisible dimension. You cannot show it on the graph. Okay, in 3D, for example.
लेकिन टाइम के साथ
Now,
तो 4 डायमेंशन होती है ना.
okay, that is a imaginative
हाँ,
kind of
different.
thing. That time is a 4th dimension, but we cannot show that dimension on R cube.
जी.
But now we are talking about another solid real number set. Okay, R4 would be what? R4 would be, let me.
It should be technically perpendicular to all the other
Yes,
3.
R4 would be R cross R cross R and cross R. Okay, till here we have 3D. Now, this will be 4D. Now, how would it look like if you try to put a picture on this board? Like, you cannot make a picture of that thing. You can only imagine it. That R4 would be a kind of space which can be drawn by making 4 mutually orthogonal lines. Because in R2 we have 2 mutually orthogonal lines. In R3 we have 3. In R4 we must have 4 mutually perpendicular lines. Okay, but here on this board I cannot plot. You can only imagine it. Similarly, R5 would be 5 mutually perpendicular lines. Okay, that is possible. It depends on the space, because it is not necessary that if we cannot plot it, it doesn't exist. Okay, if we have R10, what does it mean? R10 can be plotted in a way that 10 mutually perpendicular lines are basically, they are perpendicular with each other. That can be expressed as R10. Similarly, R100, R1000, R1,000,000, anything.
Don't we live in a 3-dimensional space?
We live in a 3-dimensional space. No, Now we are going to some abstract kind of spaces, which we cannot imagine, which we cannot see. Okay? Why we are defining this? I'll tell you later on. Let me define it first. Now, whenever we talk about vectors in n space, and we see that n spaces are R, R2, R3, R4, and so on, then the vectors are usually denoted not like this. Okay? We don't define vectors in this way. We define vectors always in column form, column matrix, okay, single column matrix. And the vectors are denoted by some small alphabet letters with the bar above it. Okay, now this is no more, if we are talking about vectors in space or Euclidean space, then we cannot define a vector in this form. This is just a three-dimensional space where we have a point. Now, when we are talking about vectors, then we always we have to write vectors in this form, in column form, okay? And this vector is denoted by small letters by putting a bar on it or bar under it. Some books, they put a bar under these alphabets. Vectors are denoted by small letters, and these are basically the components of vectors, okay? By looking at the components of vector, you can see that this vector belongs to in which Euclidean space, because it has three components, so it must belongs to R cube. Okay. Now, if we define R4, it would look like X1, X2, X3, X4. This such that all these components of this vector X1, X2, so on X3 and X4, they all belongs to R. Individually, they belongs to R, but as a whole, this is a vector in R4. Okay. So if we try to generalize this concept and write Rn, तो वो किस type की होगी? How would you write that? Rn, where n is some positive integer. Okay, where n is what? N belongs to set of natural numbers. Okay, n cannot be negative. Remember it. So Rn, where n belongs to set of natural numbers, where Rn is defined by, in this way, x1, x2, so on, xn, such that all the x's, or you can say x1, x2, so on, xn, they are individually, they are real numbers. Okay, this is your Rn. And these vectors are basically what? They are denoted by small alphabet letters with the bar on it. Okay, so this is how we define Rn, n space or Euclidean space. Okay, Euclidean spaces are basically what? These are R1 is Euclidean space, R2, R3, R4, and so on. These are all Euclidean spaces, but the elements of these spaces are now treated as vectors. Okay. If you have any question, you can ask me. Why we need to define these kind of spaces? I told you in the first lecture that we will only discuss in this part of the course linear algebra. In this course, we only discuss linear systems. Okay. In the first part, what we have discussed, how to solve linear systems. Okay. Now, when you know how to solve linear systems, now let's talk about their solutions. Okay. What kind of solutions we obtain for a particular linear system? What kind of properties, what kind of information these solutions have? What kind of information we can dig out from the solutions of those linear systems. Now, when a linear system has a unique solution, then it has a solution, unique solution. There is no further information in that thing. Okay. But when we have linear system which have infinite many solutions, then infinite many solutions are what? how do we write solutions of linear systems? They are basically vectors. Okay, solutions of linear systems. हमने कैसे लिखे थे वो? हमने vectors की form में लिखे थे ना solutions. Now, if we have infinite many vectors, then there is a lot of information hidden in that infinite many solutions. In order to discuss or dig out some relevant information from those sets of infinite many solutions, we have to know how to define vectors, how to add them, how to subtract them, how to multiply a scalar with them. So after knowing these things, we can discuss their solutions of linear systems. I hope you get it. Now, why we are trying to define these Euclidean spaces or n spaces? Because if you have a 10 by 10 linear system, and that 10 by 10 linear system has infinite many solutions, then what kind of vectors you would have in that set of solutions? You have vectors which have 10 components, each vector. So how many vectors do you have? Infinite many. So you need to dig out some relevant information about your application, then you need to discuss vectors. I hope you get it, why we are trying to define this terminology or this kind of notation and this n spaces. Any question? Kyunji? No question? So that's why we are defining these n spaces, because we are interested to discuss further the solutions of linear systems. Okay. Now, this is the general n space. Okay. This is a general n space. If I say that, let's define addition of these elements. How do we add them? How do we multiply or multiply by a scalar? So how do we define addition in Rn? Okay, in n space or Rn or Euclidean space. Okay, all of these names are of the same thing. For defining addition, we need two of elements of this space. Okay, let me choose any two elements. For example, let x and y belongs to Rn. Okay. Because the elements of Rn are basically vectors, and vectors are denoted by x power x bar. Now, whenever I say x bar and y bar belongs to n, what does it mean? It means I can write x in this way, x1, x2, so on, xn, because x is a vector in Rn, and Rn has how many components? N components. And I can write y in this way, some y1, y2, so on by n. Okay. Nobody tells me that how can I write. Whenever I see that Rn, R cube, for example, if I say that this belongs to Rn, where n is equal to 3, okay, then how would I write x bar? I would definitely write x1, x2, and x3, because I know that this n is equal to 3. Similarly, how I write y, y1, y2, y3. So nobody should tell me that how should I write these elements of the vectors. I should know it. It is obvious. Now, how to add these two elements of that n space vectors? X plus y. So how do you add them? You write x1, x2, so on, xn plus y1, y2, so on, yn. Okay. How do we add them? We add their respective elements. So their addition would be x1 plus y1, x2 plus y2, and so on, xn plus yn. Okay. And so on, xn plus yn. This is how we add two vectors in Rn. Add or subtract. If we add here, we must have to put here a plus. We can put a negative sign, so we'll have a negative sign everywhere. Add or subtract. Now, the second thing is how to multiply this vector or any vector in Rn with some scalar. Okay, that's the second thing which we need to discuss. Let me discuss now. Addition is defined in this way. Now scalar multiplication. Okay, scalar multiplication. In order to define scalar multiplication of the elements of this space, we need a scalar. For that, I say that let some k belongs to R is a scalar. Now, scalar is a simple constant. Okay? And I say that x belongs to Rn. Okay? Now, I should be able to distinguish between what is k? K belongs to R1, means k is some real number, k is some constant. Whereas x bar belongs to Rn. X bar is a vector having n components. Now, how do we multiply this vector by this scalar k? So whenever I multiply k, x by k, I have to multiply it here, and then I have to multiply the scalar with each component of that vector. So this will be k times x1, x2, x2, and so on, k times xn. This is called scalar multiplication of the vector by a scalar. Okay. So these are two basic operations of addition and scalar multiplication which we need in order to define these Euclidean spaces and spaces. We'll discuss the solutions of these spaces in the next lecture. Sorry, some other operations and properties of these vectors in the next lecture. I hope you got these things. If you have any question, you can ask me.
सर ये नई वाली प्रॉपर्टीज प्लीज क्विज में ना डालिएगा.